Welcome back, Quantitative Analysis 2 students. We're going to carry on with our derivative studies, and we're going to do some more advanced derivatives today. We're going to study the product rule and the quotient rule and the chain rule. And the product rule and quotient rule you'll find to be basic algebraic templates. However, they do require you to, again, show mastery of things like square roots and fraction exponents and things like that. But then when we get to the chain rule, it's a little bit deeper. And when we get to that position, I start explaining the chain rule, you might find yourself a little bit lost. And if you do, speak up and let me know, I can clarify again. But I do have a general experience with the chain rule that usually people don't get it the first time you explain it, but they at least buy into it, and it's an easy tool to use. After you use it for a little while, the chain rule, you start to realize it represents composing functions, which is another topic from your algebra nightmares in the past. But ultimately, the chain rule is one of those kind of out there calculus ideas, and it's if you don't see it the first time, believe me, if you keep studying it and read the chapter and do the practice and watch the video again, it will start to become clear and you'll start to understand a little bit more. And that's what I got to say for you guys about the chain rule. And the best way to apply the chain rule really is to look at how it applies to the power rule, because the chain rule can be used for a lot of different other rules, but the power rule being our initial rule and the easiest rule we know, it's easiest to show how the chain rule works using the power rule. So that's going to be the second half of our lecture. Today I do plan to go all the way until 6:45. If we get out a little bit early, that would be great. I would like to, but I'm not going to rush it. This is the kind of thing that we do have to kind of spend some time on. For the first time today in our class, we're going to use a chalkboard that I've devised using my tripod and my iPhone and some construction paper and a marker. I'm going to attempt to do some math with you guys live instead of taking pictures of it and then sharing it. And on that note, before we start this lecture, I'd like to just kind of return to something that we did once before, last time, where we talked about some basic derivatives. Let's just review that for a minute. All right. These are some derivatives that we did in the last one. When we were together on Monday, we studied the power rule and the constant rule. We also studied the coefficient rule, and then we did the sum and difference rule, which are all the most basic derivative rules, introductory. These three examples represent all those rules, and at this point in the game, we are kind of assuming that you are experts at this. If you have issues with this, that's still totally understandable. Believe me, this is no piece of cake at all. But today, our lesson about the quotient rule, the product rule, and the chain rule, if you don't really have this down, you're going to feel very lost today. So again, if you felt like you're a little bit of trouble with this, let's just review this for a minute, and then we'll go ahead and begin our lesson, because I think it wouldn't hurt to just kind of review this. This might take maybe 10 minutes. All right. First, let's look at example 5a. In example 5a, you have a basic monomial 4x to the fifth. The concept is you take the exponent that you see up here, the 5, and to find the derivative of this function, you take it and make it the new coefficient. So you see the derivative, which has f prime, has a little notch there. This is f of x. This is its derivative, f prime of x. F prime of x would be, start with the exponent, the 5. So we have a 5 here, and then, oh, I'm sorry, the x, start with the constant, my bad. Let's start with the constant. The constant that is here, the 4, you kind of ignore it for a minute. That's what the constant rule says. If you see a multiplier, you can ignore it for a minute and do what you see here, the x to the fifth, and then come back and bring the 4 in. So it looks like this in math when you write it. Okay, so I'm going to ignore the 4, and now I'm going to do the derivative, which means take the exponent 5 and bring it to the front. There it is. And then lower the exponent by 1, making it a 4. That's why now, basically, this is the associative property that these two can be thought of as one little product. 4 times 5 makes 20, and then you have this as your solution. So in short, the derivative of this is this, and it should be very elementary how to come up with a derivative. A lot of students do the quick shortcut of 4 times 5 makes 20, and then reduce the 5 into a 4, and then you got your 20x to the 4. Now, of course, in the case of simple numbers like 4 and 5, it's obvious. But when you look at weirdos like fractions and square roots and stuff, what happens is you have to recall an even more previous lesson back in maybe 9th grade, where you learned about how to play around with negative exponents and the concepts of fractions you learned back in 4th and 5th and 6th grade. Those old math topics come back to haunt you in calculus that way. In example 5b, we have a great example of the constant rule involving a fraction. So we can't run away when we see fractions. You cannot change fractions into decimals because you're afraid. You have to face them head on. They are not as horrible as you think, and I'm here to help you with them if you have issues with them. We can talk about them all you want. I can help you understand them. They're really not as hard as they make them. They have a bad rap. In this case, the 1/2 is here because it happens to push together very nicely with the new coefficient, which would be 2. So in the case of a constant coefficient, 1/2, we would take that 1/2 and ignore it for a minute. So I just write it and ignore it. And then I think about t squared. What is the derivative of t squared? It would be 2t to the power 1. And now 1/2 and 2, of course, come together very nicely to knock out, and you're left with just t to the 1, which we all know t to the 1 is also known as t. And in math, we try to give the most simplified answer. For example, t to the 1 could be simplified ultimately to just t. Last but not least, we have the nightmare of square roots and denominators. First of all, since this is in a denominator, if this was q to the 7th power, this would be q to the -7. If this was q to the 48th power, this would be q to the -48. So in other words, when you see something in the denominator that has a power, you can write it as if it is not a denominator and just make the exponent negative. It makes opposites happen that way. Likewise, the fact that we have an exponent of 1/2 comes about because this is a square root. The square root means 1/2. So ultimately, before we see this, you might interpret this to be 5 over q to the 1/2. Let me write that. Right? And if it's 5 over q to the 1/2, then this q to the 1/2 can be brought up such that it looks like this. You see what I'm saying? Now, likewise, the 1/2 is there because we do have 2 specific important measurements on the q. We do have that it is q to the 1 power, right? And likewise, we do have that it is a square root. And another bonus math fun trivia idea is, if you don't see an index there, then you assume the index is 2 because it's a square root. That means ultimately the exponent is the numerator, right? And then the index is the denominator. So we can't really take derivatives of square roots. We have to first rewrite any function that has square roots or cube roots or any kind of root in terms of variables with exponents, negative and or fractional exponents, so that they can fit into the mold of how to find a derivative with the power rule. And the power rule now being -1/2, we still follow all those concepts. 5 is going to be just ignored for a minute because of the coefficient rule. And then we have q to the -1/2. So -1/2 is the new coefficient. And then this has to be lowered by 1. So we take -1/2 minus 1, and we get -3/2, and that's why this is what you have. All right. Now there's a couple ways you could rewrite this. This is probably the most direct and simple way to write it. All right, I hope that's clear. We need to know those things because the next couple of lessons we do are going to involve a lot of this material. Something else in here that I'd like to talk about before we go on. There are some little things in math that I just want to remind you of that might make things easier as you're carrying on here in quantitative analysis too. One of them is, if you ever have a number and you have to subtract 1 from it, this might go on in your mind, because you learned how to subtract fractions back in middle school and grammar school. But even so, I want you to remember that the number 1 can be written as anything over itself. It could be 2 over 2. It could be 7 over 7. It could be 91 over 91. It could be x plus 8 over x plus 8. All of these fractions are 1. So whenever you're trying to add, and later on when we do integration, you'll be adding 1 to numbers often, for example, fractions. Whenever you have to add or subtract 1, make it very simple and convenient for yourself. Always use the denominator that makes it as easy as it can be. We need it to be 2, so make it 2 2s. Now, what is -1/2, -2/2? Can you see now that it's -3/2? In fact, it becomes very clear and simple that it's -3/2. This works with any horrible fraction. 7/19 minus 1 is going to just use 19 over 19 then. Okay, now what is 7 minus 19? Don't be shy. It's not that hard. It's -12. There you go. So you got to make these things elementary and quick and simple and painless. When you add or subtract 1, use that concept. Take advantage of the fact that you can devise any fraction you like that's equal to 1, and it's easy to do. Use the one that you like because you're trying to combine it with a half or a 19th. 19 over 19 is what you should use then. And believe me, when you get to more advanced homework, you'll start doing things like 19 over 19. So just get ready for that. Adding and subtracting 1, friends, is supposed to be real simple. Let's make it easy. All right. That's one of the most important ideas I wanted to share with you. The other idea I wanted to share with you guys before we move on is this concept of our calendar. And in our calendar, please be advised, and let me take back the, hold on just a minute. Here I am. Okay, I'm just trying to navigate through. Anyway, basically, this is our calendar, and I did want to share this with you to talk for just a minute about where we are in our course. Today, we're going to attack chapters 9.5 and 9.6. Last time we did 9.3 and 9.4. There is a video. You can watch it if you missed it, and it's the same thing with the lecture 9.1 and 9.2. Your exam is scheduled for Monday, so please make sure, my friends, that when Monday comes at 4:30, you're ready to take the exam. If you need to take it a little bit later, that's okay. I've left it open for you late, and you can take it up until 9 o'clock. That means if you could start at 7, it'll close at 9. You have a 2-hour window once you open it. Tomorrow at 4:30, I will be here online. There will be no lesson, and you don't have to come if you don't want to, but I'm going to be here if you need me to go over any questions from the web assign, to go over any questions from the exam number 1 review, to go over anything having to do with our textbook or our PowerPoints or our videos or any of our discussion questions or anything you want to ask about. That's what tomorrow is about, anything you may need. There's nothing coming from me, it's all coming from you. If you guys have nothing to talk about and you're ready for your exam on Monday and you don't want to come on Thursday, that's okay, I understand. But please know that's what our plan is for tomorrow, is only whatever I can do to help you. Come with questions. As you're studying and learning, bring them tomorrow. And if you have anything you want to talk about, that's what it'll be. At 4:30, I'm going to be here. If 4:40 comes and nobody comes at 4:30, then I'll assume you guys are okay, and then I'll leave too. But if you guys are here at 4:30 and I'm here, we're going to study. So please don't come at like 6 o'clock saying, why wasn't everybody here? We're meeting at 4:30. And if you want to be there, you got to be there at 4:30. Otherwise, you won't be part of the conversation. Okay? So that's everything I wanted to share with you. And I think now we're ready to start our lesson. So let's go right in to our lesson, which is going to be about the power rule, the product rule, the quotient rule, the chain rule, and then the power rule. Starting with the concept of the product and quotient rule. Now let's recall those words, product and quotient. What do they mean? The product is the answer to a multiplication question. 3 times 7 equals 21. 21 is the product. And then we have the quotient rule. The quotient rule is the answer to a division question. So for example, 100 divided by 20 equals 5. 5 is the quotient. What is the point of these rules? Well, remember how we discussed we have some basic rules in calculus that we've studied with derivatives. We have the power rule, we have the coefficient rule, we have the constant rule, we have different rules about adding and subtracting that you're allowed to do. And then we studied some little axioms and ideas about negative exponents and square roots and stuff. But we never did really attack the concept of what if I have one function times another function? Or what if I have one function divided by another function? And basically now what's going to happen is we're going to see how you can go and find derivatives of functions that don't really fit your old mold of a power rule or a constant or a coefficient. Okay, so the product rule and quotient rule, here they are. They're written, in my opinion, it's not as challenging as the way they've written it. I'd like to share with you the way I learned it way back in 1990, oh geez, I don't know, 92, I guess. When I took calculus, we used F and G. And if I explain it with that, to me, I feel like that's a little bit easier to understand. So let's take a look at it that way. First of all, let's talk about the quotient rule, okay? The quotient rule works this way. Not the quotient, the product rule. The product rule works like this. Let's pretend for a minute you had a product and that your function was actually in the format of a product. Okay. So this is x squared times 2x plus 5. That is a product. Now, if you wanted to consider that these two things were two different functions, as if this was f and as if this was g, then you could kind of go about figuring out the product rule. Here's what the product rule says. If you have f times g, and you're taking the derivative of it. Basically, you can multiply them together in this fashion, such that you have f prime g and f g prime. In other words, in this one, there's one primed, in this one, the other one is primed. And it doesn't matter which way it goes, if you want to do this one first or that one first, if you want to do this g prime f, or any way you want to write it, but as long as you get the concept that we're going to have a combination of this times the derivative of this, and then this times the derivative of this, right? And add them. That is the product rule. So if we did it to this one, we would start by saying, well, I guess f in this case looks like x squared, and g in this case looks like 2x plus 5. Great. So what therefore is f prime? You might recall learning yesterday, or was that Monday, that when you have a power rule like x squared, this one is elementary. You take the 2 goes in front, you copy the variable, you think of 2 minus 1, it makes a 1, and then of course that does boil down to just 2x. So the derivative of this thing is this. Here, the same situation goes. We have a coefficient here. So to find g prime, we're going to just write that coefficient first and then multiply. And then we say, what is the derivative of x? Well, the derivative of x, in case you forgot, is going to be just 1. And the reason why is because if it's x to the 1, then the derivative of that is going to be 1x to the 0. And remember, x to the 0 is 1. So guess what you get? 1. Anyway, the derivative of x is 1. That being the case, this turns out being 2 times 1. And now how about this thing right here? What happens when you take the derivative of 5? Recall the constant rule. The derivative of any constant, is going to be 0. So the derivative of 5, therefore, is 0. In other words, g prime is simply 2 times 1, or 2. Now, let's go ahead and construct the derivative using the product rule. F prime g means this times this, right? And then fg prime means this times this, which is 2x squared. This is our derivative. Now, of course, you want to do the right thing and distribute and simplify and do your algebra right. This is now 4x squared plus 10x plus 2x. Let's do the right thing and combine those like terms. They're 4x squared plus 12x. All right. So when you're asked to find a derivative, and it kind of looks like it's in this format, such that you could identify it as one thing times another. Identify f and identify g, and then find f, rewrite f and g, then find f prime and find g prime, and then follow this construct and put them in position, and then simplify with your algebra skills. And you get something like this. We can look at it as f and g. I like it that way a little bit better. Your textbook is using, and let's return to our conversation here. Your textbook is using u of x and v of x. U and v are very, very similar looking. If I was using u and v, I don't know how clear that would be, you know, which one is which when you're trying to look at them. F and g kind of feels a lot easier to interpret. Now, that being said, if you look, we'll see the quotient rule is not that far away from the product rule. In the case of the quotient rule, we do have a similar situation where there's an f and there's a g. In this case, u over v instead of u times v. So if we do it, you know, you go and find u prime and v prime, or in our case, f prime and g prime, and then you just put them into this odd situation. Again, all of those x's in there, and the fact that they're using u and v. I'm sorry, but I disagree. I think you should use letters that are clearly very different. U and v are very similar looking letters. I don't think we need of x everywhere over and over again. I think that dulls it and makes it harder to interpret. So I'm going to show you how I would do the quotient rule using f and g. In the same case, here comes the quotient rule now. The quotient rule would be, if I had the derivative of f over g, if I had a function that looked like f over g, like say, for example, it was there you go. Let's say that was your function. You're trying to find the derivative of something kind of like this. Obviously, it's a quotient. It looks like a fraction. Well, if you are trying to find the derivative of f over g, the way you got to do it, and this is kind of important, you have to make sure that you do the derivative of the top thing first, like this, f prime g, and then put the minus. And the reason why you got to do it that way is because when it comes to the product rule, you know that addition is commutative. In other words, it doesn't matter if I put this first or that first, you know. But in the case of the quotient rule, there's a negative sign, there's a minus there. It's significantly very different and crucial that you make sure that you use the derivative of the first thing first. The top thing gets the derivative first in that situation. So that's why it would look something like this. And then over g squared. And that's a little bit funny looking. But what that really means, friends, is you're just going to take g the way you see it, however hideous and huge it is, for example, x squared minus 8, and just slap a parentheses around it and put squared and you're done. Okay, so in this situation, if we were finding the quotient rule using a formula like this one, we would start by identifying f and identifying g, and then we'd use our calculus to figure out the derivative of f. And this time, I think you might recall, before we had something similar where we were trying to figure out the derivative of 2x, and remember, where was it? The derivative of 2x, there it is. We're trying to find the derivative of 2x, wasn't it just 2? In fact, there is a little bonus theorem here. If you have a constant times x and you do the derivative, you just get the number itself back. So the derivative of 7x is 7, right? Okay, you can remember that. What's the derivative of 78x? It's 78, okay? And then here, a similar situation with g prime. We're going to do the x squared, which, by the way, at this point, you'll do it so many times, you'll start to remember x squared makes 2x, you know? And then what's the derivative of negative 8? Don't forget, the derivative of any constant is 0, so it's going to evaporate. And now I have f, g, f prime, and g prime, and I could put them all together to figure out what the derivative of h would be. It would look something like this. H prime of x, and you got to give yourself a lot of room because this is going to take up a lot of room on the paper. H prime of x is going to be f prime g, which is 7 times this expression, x squared minus 8, minus fg prime, which is 7x times 2x, all over g squared. G is this expression here. So it would look like this, x squared minus 8 quantity squared, like so. Now this right here might raise a little red flag if you remember learning back in algebra. You write this twice and multiply it out. In the case of using the quotient rule, often you're not required to multiply this out, so just leave it. Even if you have a trinomial in here, like x squared plus 2x plus 1, you could just put a parentheses and squared and leave it. That's enough. With the quotient rule, it already is such a big mess that simplifying this is really wasting your time. This is acceptable, and WebDesign will take it just like this. However, up here, you might want to do some distributive property and combining. In this case, there is no distributive property. This is just all associative and commutative property stuff. So let's do this. This is distributive 7x squared. I'm going to come over here and finish it. 7x squared minus 7 times 8 makes 56. Remember that from your times tables. And last, 7 times 2 is 14. And x times x is x squared. So this is minus 14x squared. I'm running out of paper over there. And then all over that nasty denominator. And one more thing, 7x squared minus 14x squared is actually not hard to do. That is negative 7x squared. And here we have our solution. This is the derivative of this function. Now, ultimately, we just went through a lot of work to find derivatives of very ugly functions. What is the point of all this? Well, let's not forget what a derivative is. A derivative actually is a formula for a slope for a line that is tangent to this function. So, for example, if I graphed this, or if I graphed this one, if I graphed any of these, and I picked any arbitrary point on here, and took the x value and put it into the derivative here, it would tell me the slope of the line that is tangent at that point. It also represents the margin, or the marginal, whatever this function is. If this function is a cost, it's the marginal cost. If this function is the revenue, etc., and profit, they have their corresponding margins. You can find that using. Also, we can talk about the average rate of change and instantaneous rate of change. That's another thing that applies here. So the reasoning behind all of this math is to be able to apply it to physics and to economics in those ways, but this is the backbone of it, and we need to be able to do it on paper, or at least understand it on paper to be able to get some solutions. So let's come back to our conversation. And in here, we have a nice display of both the product and quotient rule. And I'm hoping you'll come back here when it's time to find derivatives of products or quotients. Likewise, if it helps you, you could come back to my study guides and use the F and G situation. That's up to you, however you think you'd like to do it. So let's carry on with the PowerPoint. So let's go ahead and use the product rule to solve some derivatives here. By the way, we do have a couple of different ways that you could say the derivative, and I think we should talk about that for a minute. Let's take a look at A. It says find, and there's a funny expression there. I just want to clarify. The way we say that out loud in calculus is dy dx. You might think it's dy over dx or something else like that. The D does stand for a differential or derivative, or difference. And when we come to finding the derivative, slang for it is dy dx. And I just want to kind of give a little conversation about that for a minute. In the realm of finding derivatives, if you had something like y equals 7x squared plus 2, if you want to find the derivative of this, you can do this a lot of different ways. You could call this y prime. You could call this dy dx. You could call this capital D with a little x down here. Still, there's even more ways, and different textbooks have other different ways to show, but these things all mean the derivative of y with respect to x. And when we say the x here, this letter came because it's in terms of x. So a nice comparison would be something like p equals 14q minus 1, something that might be an odd demand curve or supply curve, something like that. If you were finding the derivative of this, it would be dp dq. And that's because we started with p, so it's dp, and it's with respect to what variable? The variable of q. And in a minute, you're going to see what that means with respect to q. In other words, q is the variable in this case. Everything else is a constant. The only thing that will vary is a q. We might sometimes see other variables in there that are constants, and we promise you it's a constant. And if it's a constant, you have to treat it like a constant, which means the derivative of it is 0. If it's multiplied by x, you don't use the product rule, you just use the coefficient rule because it's a constant. And that's going to come up in a minute when we do an example like that. But when it comes to with respect to, it's the variable in question that you're doing derivatives to. And usually 99 times out of 100, it is x. Most of our functions look like this. And further, if you had a function that didn't have y, but instead it was calling it f of x, and you were finding the derivative of it, you could call it f prime of x. Or if you want, you could just call it f prime. That also is nice. Okay. All right, so I hope that helps a little bit. We do need to be clear with that language, because I found when you're studying calculus, if this all is not made very clear, you keep looking at things that you already know, but you can't interpret them because they don't exactly tell you all these tricks. This is something that I want you to hold on to. These are all the different ways you can write the derivative is. You can write y prime equals dy dx equals capital D lowercase x equals. I don't even think they use this in your book. You might not even see it in your book, but you see this in other books too. Same thing with f of x. The derivative is f prime of x, or it could be f prime only. All right. So they're saying find dy dx at this specific special, with this formula, and then find it at this special point where x equals 1, find the slope of the tangent to this graph. Now, we have two different functions there. I'm going to do one at a time, and I'm going to do them through the chalkboard. Let's jot them down first. Nice. First, this is example 1A. And we got y equals 2x cubed plus 3x. If you have a notebook and pencil and you wanted to do it along with us, I recommend it. It'll help you out a little bit to actually have some hands-on, while you're doing it. All right. I'm going to also set myself up with the other one. Let me just jot that down too. Example 2, example 1b, and it's 4x cubed plus 5x squared minus 6x plus 5, x cubed minus 4x squared plus 1. Okay. All right, great. Let's tackle these. Here we go. We're trying to find the derivative here. And recall the product rule, and I'll have it here for a minute. Here's the product rule again. It doesn't hurt to rewrite it. I like to write formulas before I start to do math, so I'm going to jot this down on the red paper first. The product rule goes this way. F times g, when you take the derivative of it, is going to be fg plus fg. And in one of them, we're going to prime the first one, and the second one will prime the second. Now, let's go ahead and define f and g first. Okay, so f will be this first thing in the parentheses here. I'm going to give a little note that this is f here. All right. And we've got 2x cubed plus 3x plus 1. This right here, this is going to be g right here. Right? And so g is x squared plus 4. Great. Now, let's find the derivatives of these things. F prime will be the derivative of this little expression. 3 times 2 makes 6, and then lower the x cubed to x squared. By the way, we're allowed to do the derivative to each of these 3 different things because of the sum rule. Remember, the sum and difference rule is telling you that if you have a function like you see here, you could take the derivative of each little thing as you go through. So the first thing we did was the derivative of this. It's 6x squared. Next, the derivative of 3x. Remember the little bonus theorem I gave you? Here it is, right? Remember this one? The derivative of a constant times x is just that constant. So what's the derivative then of 3x? Going to be 3, right? And last but not least, what is the derivative of 1? Remember the constant rule? The constant rule says the derivative of a constant is 0. Okay, so then the derivative of that is 0. In other words, that plus 1 just evaporates into thin air. That is f prime. Good to know. Let's carry on with g prime. G prime is going to be, again, with the sum rule, I'm going to do x squared, then I'm going to do 4. So what is the derivative of x squared? Didn't we do that at least 3 times today? It's going to be 2x. And what is the derivative of 4? Remember, it evaporates because it's a constant. The derivative of 4 is nothing or 0. So now we have f and g and f prime and g prime. So what we could do is we could now construct the derivative using the product rule. Let's do that. If this was y, we're going to now tell you what y prime is. Here it comes. It is kind of important in math to tell me what you're given. What I write here is not equal to this. So you don't want to write y equals or just equals. This is a new thing I'm writing. This is the derivative. It's y prime. Y prime is going to be first f prime, which is this expression, times g, which is this expression, plus now f, which is this whole expression. Use parentheses. It makes everything look very clear. Use parentheses. And you know what else? Try to write really neat. That also helps a lot. Last, we have g prime, and g prime is simply 2x. Okay. All right. So now you have a nice little 9th grade puzzle to solve. I'm going to do them like they're 2 separate questions. First, I'm going to do FOIL to this. Do you remember the FOIL method? FOIL method happened back in 9th grade, probably in October. FOIL method says first, outer, inner, last. This is the first pair. 6x squared times x squared, that's 6x to the 4th. This is the outer pair. 6x squared times 4, and that's 24x squared. This is the inner pair. 3 times x squared makes 3x squared. And this is the last pair. 3 times 4 makes 12. Also, of course, we're going to be able to combine these. But before we do that, let's also finish this piece out because there's probably stuff in here that could combine with this later on too anyway. So before I carry on with the plus and this stuff, all I did here was our old FOIL method from October in the 9th grade Algebra 1 class, where you do first, outer, inner, last. Here's the 4 things that you write out. Now what we'll do is we'll apply the distributive property here. It's not as clear because usually the distributive property has 2x right in front, but here it's on the end, and you probably saw this in textbooks. Welcome to calculus. We like to go backwards a lot. Okay, so we're going to use 2x and multiply it by each of the things in the parentheses. 2x times 2x cubed. Remember, this is 2x to the 1 in there. So the thing is 1 plus 3. It's going to be 4x cubed. 4. Wait a minute. Yeah, 4x to the 4th. My bad. 4x to the 4th, because it's 3 plus 1. Likewise, we do 2x times 3x, and that is 6x squared. And last 2x times 1 is 2x. By the way, if you can't see that, sorry about that. That is a 4 over there, my bad. That's supposed to be a 4. All right, so it looks like we've got a whole long list of terms. Let's now collect them and make them into one nice polynomial that's in descending order, like we did back in Algebra 1, starting with the highest exponent, which I see being 4th power. So 6x to the 4th plus 4x to the 4th is the first thing I'm going to do. That's these. And that does make 10x to the 4th. The next power down that I see, yeah, I guess there's no, did I miss one? I didn't miss one, did I? I did. Damn, I did. This is 4x squared. Oh, wait, no, I didn't. No, I'm right. I'm doubting myself. Okay, sorry, guys, I'm doubting myself. Yeah, I'm doubting myself. Anyway, there is no x cubed term. I just wanted to double check it. There's no x cubed term in here. It looks a little funny, but there's not. However, there are x squared terms. We have this one, and of course this one as well. So it's 24, and 3 makes 27. 6 more makes 33. Last but not last, we do have actually 2 more terms to go. We have a x term, and we have a constant term. This is our derivative now. And this is all the work you got to go through to get the derivative. Note, we have ugly coefficients. We have large exponents. Welcome to calculus. Don't be afraid of that. Sometimes back in math class, you would look and say, wait a minute, 33? I don't think that's right. No, you're right. You're on the right track. Usually they're very uncomfortable numbers. They're trying to show you the most advanced kind of math. Okay, so I hope that makes sense. I hope that helps. That's a great example of how to use the product rule. Let's use the quotient rule now. Here's the other case in our lesson today where we're trying to find, oh, well, we're not using the quotient rule, we're using the product rule again. Great, well, we're gonna need practice with it. Let's do another one, that's just fine. So let's go ahead and do another one. Here, we have an obvious f and g. We're gonna make the f, of course, the first thing. And then, of course, we're going to make the g the second thing. All right. Now I've got 2 functions, f and g. Great. Let's go ahead now and find the derivatives of those 2 things. That would be f prime. And here, remember the little coefficient and power rule trick? 3 times 4 is the first idea. We do 12. So 3 times 4 is 12, and then write the x. Now lower that x cubed, it becomes x squared. Next, we think of 5 times 2, that makes 10. And then we lower this x squared, it becomes just x. Remember this little rule with the a that I used? Where did I put it? Where is it? Here it is. Remember a to the x, the derivative is, not a to the x, a times x is a. So the derivative of negative 6x is just negative 6. There you go. All right, then we got g prime. And in g prime, we have x cubed, which is 3x squared. Then we have negative 4x squared. So 2 times negative 4 makes negative 8, and that's x. And the derivative of 1 is a constant. The derivative of 1 is going to be 0. Remember that rule? I'll keep bringing them back, keep reminding you to help you learn it. Because it's a lot. This is a lot of stuff. What's the derivative of a constant? It's going to be 0. All right, so now I have f, g, f prime, and g prime. Let's go and construct the derivative now using the product rule. So it would be the derivative of f times g prime is supposed to be fg plus fg. And if you do it this way, you never have to memorize it. You'll always remember it. I mean, you'll never have to go look at it again. You'll find yourself memorizing it. That's what I meant to say. Anyway, so it's f prime g plus fg prime, and now that would be this expression. And by the way, if this is y, I'm going to show you y prime now. It's this expression, f prime g, which is this expression, plus f, which is this expression. And now look, I'm running out of room. Here's how you deal with that in calculus. Keep on writing, but start around here. 4x cubed plus 5x minus 6x plus 5 times g prime. G prime is this expression now. 3x squared minus 8x. All right. Now, I mean, you got a real algebraic mess going on here. There's a lot of terms here. There's a lot of work. It'll take maybe 5 minutes or so to go through it. I'd like to go through it with you and show you how you would go about doing it. What you have here is the actual derivative, and we could simplify it, but I want to just direct your attention briefly back to our question before we carry on here. Notice that it says here, and let me come back in the conversation here. Okay. Notice that it says here, at the point where x equals 1, find the slope of the tangent line to the graph of. Now, guys, look closely at the question. Do we need to simplify this? Actually, no, we don't. In fact, we can get away with not having to simplify this. I want to really just highlight that and make that really clear for us. When you are doing calculus homework, you have to read the word problem very carefully. You'll find yourself doing a lot of work you don't have to do. Look at what it says. At the point where x equals 1, find the slope of the tangent line. In other words, find the derivative, and then after you find the derivative, plug in 1. So do we need to simplify this? Nope, we don't need to simplify this at all. All we need to do is take it just the way it is and put 1 in there and see what we get. So let's put 1 in there. A nice way to write that is y prime of 1 equals, and then in every position here we put a 1. Now you can probably in your mind's eye see what this becomes. All of the x's become 1. X squared is 1. 1 squared is 1. 1 is 1, right? 12 times 1 is 12. So this is really 12 plus 10 minus 6. It's actually really not hard at all. It's 16. Here, if I put 1s in every position, I get 1 minus 4 plus 1, which is negative 2. Here, if I put 1s in every position, I'm going to get 4 plus 5, that's 9, plus minus 6, that's 3, plus 5, that's 8. And if the x was 1, this whole expression would just be 3 minus 8, which is negative 5. That would be negative 32 minus 40, that's negative 72. So it's not just algebra, it's also very tricky, mean critical thinking. You have to look at it and not always, I mean, in your gut, you're probably thinking, oh, I got to multiply all that out. And the best thing about it is, no, you don't. You just have to answer the question. The question is saying what happens when x equals 1. Put 1 in there. Now, if you get negative 72, right, and that's not the right answer, what does it mean? Well, it means that you probably did everything right, except this should have been a plus. Or you forgot, or you made a silly mistake thinking about 4 times 5, and instead of writing 20, you wrote 25. Things like that will happen, and that is probably the most common mistake that people make when they're doing derivatives, is simple little basic times table facts, negative, positive facts that you really know, but that you're just in the middle of so much nasty algebra that you kind of lose sight of for just a second in your journey through all of this muck to get to your final answer of negative 72. The answer is probably not 72. I mean, I hope it is. But if it isn't, it means we would come back in here and take a look closely and find out what went wrong. So anyway, I'm going to cross my fingers and hope I did that right. Well, let's take a look now at what the answers are. I do have them here for us. That does look familiar. I know that we had that before. That was the answer to this one. Here it is. Right. Oh, where is it? right? I just had it, isn't that funny? I love that, guys. Here it is, for example 1a. All right, so for example 1a, this is what we got. You have 10x to the fourth plus 33. Great, so we got it right. Hard to believe, right? All right, let's take a look at the next answer now. Negative 72, right on the nose. Bingo. It's hard to believe I got that right. See, now you have a new respect for me, don't you? Yeah, now you think I got brains. All right, I'm just kidding. All right, let's look at a couple of them that have to do with the quotient rule now. And as you could see there, we have two cases of the quotient rule. And let's mention once more that idea of we're not asking in part B for the actual derivative itself. We're really more so asking about the derivative at a specific value. You know, we want it right there at x equals 3. So for part B, what we're going to do is we're going to go ahead in there, find the derivative. It's going to be a little ugly. And then when we're done, we're going to replace 3 in for x and see what we get. Okay. All right. So let's take a minute now and jot them down. First one looks like this. And then the last one looks like this. So for this one, we're going to ask you to go ahead and figure out the derivative f prime of x. Notice this is a quotient. Let's rewrite the quotient rule once. F over g prime. If you're trying to find the quotient here, don't forget that the bottom is g squared. I think you probably remember that. Some students write that first. Now, we got to make sure that we do FG. But remember, we want the derivative of the f to be the first one. So it's f prime g minus f g prime. Okay, this is the quotient rule. I'm going to apply this now to this function as if f was the numerator and g was the denominator. Now, let's find the derivatives of these little expressions. F prime, the derivative of x squared. How many times are we going to ask you? What's the derivative of x squared? 2x. The derivative of negative 4x, I think we got it, right? That's the coefficient with the a thing I showed you, is negative 4. Now g, what is the derivative of g? G prime, what's the derivative of x? Let's not forget, the derivative of x is 1, right? Every time. So, right? And then what's the derivative of 5? Don't forget 5 is a constant. Derivative of any constant is 0, so it evaporates into thin air. Now, let's go ahead and write out the derivative. We're going to apply the quotient rule. So we're writing the derivative. The derivative is called f prime of x right now. F prime of x is going to be, according to our formula, f prime, which is this, g, which is this, minus f, which is this, g prime, which is 1. Okay, all over g squared. What's g again? G is this thing. Now, like I said, you don't need to necessarily multiply this binomial out, x plus 5 times x plus 5, and write it. But up here, you might want to do this. You know, it depends on how far they want you to go with your solution. So here I would do a FOIL to this thing, right? And that would look something like this. I'm moving fast through this because I'm trying not to insult you. I know you learned this in 9th grade, but that's FOIL right there for you. And now this 1, there is a property, the identity property of 1. It says that 1 times anything is going to just be that anything again. You learned that a long time ago. So we can just act like that 1 isn't there because 1 times this is just this. But remember, there is a negative 1 here being distributed. So negative x squared plus 4x. Again, all over that pesky denominator of x plus 5 quantity squared. Now, can we combine anything? Well, I do have one 2x squared term there. Then I have negative 4x and 4x. They cancel out very nicely. Oh, look, I do have a negative x squared. These come together. So it's really actually, sorry, x squared. Because this is negative 1. 2 minus 1 is 1. It's 1x squared. The 4x and negative 4x cancel out. I have 10x and 20. And then on the bottom, I have x squared. I'm sorry, well, I have x plus 5 quantity squared. This is the derivative we're expecting you to come up with using the quotient rule for this function. I hope that makes sense. If you wanted to multiply the bottom out, it would look like this. And then you'd multiply it out, you get x squared plus 10x plus 25. All right. And you could put that here instead if you wanted to. Notice, even though they really look like they'll cancel out, they won't. Let's write that out, actually. Let's just write that out for a minute. Even though it really does look like it'll cancel out, it really won't. I'm going to use the back of something else for me. Say you did write this, right? And this is an important topic in math I want everybody to be really familiar with. If you thought this was your solution, and on the bottom you wrote out close look at that for just a minute. Don't you feel tempted to slash out those x squareds? Don't do it. You can't do it. Why can't you do it? Why can't you do it? All right, I'll give you a great example of why you can't do it. Here's one of my favorite fractions. 1,000 plus 2 all over 1,000 plus 1,000. This fraction right here is 1,002 over 2,000. It's almost a half. Almost. If I did this, look at what it becomes. It becomes 1 over 500. 1 over 500 and 1 over 2 are very, very different. In other words, you may not cancel them out because there are plus signs. If they were multipliers, then yes, of course, please scratch them out. But there's plus, do not cross them out. And if you do, you'll find yourself going down the wrong road and you'll start getting stuff wrong. Very common 9th grade math snafu mistake. All right, let's do the next one and then we'll take a little break. The next one, we're asked to find the derivative, and then when we're done finding the derivative, we'd like to know what happens at the moment of x equals 3. So here we're going to again apply the quotient rule. I always like to have the formula for reference on the page with me when I'm studying. So let me just take a minute and write that again. It'll only help to refresh it in my mind anyway. The derivative of a quotient f over g would look like this. It would be fg minus fg all over g squared. And don't forget to take the derivative of the first thing first, like so. So now I'm going to have to define f and g, and then find f prime and g prime, and then assemble the quotient rule here, assemble the derivative using the quotient rule here. All right. So first of all, f is the numerator, x cubed minus 3x squared plus 2. And g is the denominator. It's x squared minus 4. Now the derivatives, f prime, here that would make 3x squared minus 6x. And g prime, here that would make 2x. At this point, I'm not going to explain the same thing over and over again. I know you already saw me explain it a couple times. I don't want to bore you. But there are a lot of beautiful little theorems in here that are coming through. The quotient rule has in it the power rule and the constant rule and for the two. And the other rule was the coefficient rule. They're all in there. Next, let's assemble the derivative using the quotient rule. We're trying to find f prime of x, because this function initially was called f of x. F prime of x now is going to be, as our formula tells, f prime g, which is this expression, times this expression, minus fg prime, which is this expression, times this expression. Barely got it in there. Barely got it in there. Okay. What else? Did I forget something? Yes, I did. The formula also has g squared. Let's put g squared on the bottom. G is this. Especially when you see an exponent in there. You don't want to FOIL that out. You know, leave it x squared minus 4 quantity squared is more than acceptable. Now, am I going to multiply this all out and do all this? No. Remember what the question was. The question was, what happens to this function at the moment x equals 3? That means I'm putting a 3 right here, and here, and here. And also I'm going to put a 3 here, here, and also in here. And don't forget, I got to put one also right there. So 3 times 3 times 3 is 27. 6 times 3 is 18. 3 squared is 9. Do it in steps. You don't have to do it all at once. X cubed is 27. 3 times 9 is 27. These knock out. It's just 2. And 2 times 3 makes 6. And on the bottom, it's again 9 minus 4 squared. I'm almost done. I just have some basic arithmetic to do now here. This right here is 9. This right here is 5. 9 times 5 is 35. And then 2 times 6 is 18. And then 9 minus 4 is 5. 5 squared is 25. What is 35 minus 18? 17. So our solution is 17/25. Ugh, it's pretty ugly. 17/25, that's the answer we were looking for. 17/25 also can be translated into 68% or 0.68. Let's take a look at what the answers were that came out. Our first one, I think we discussed that's what it would be, and we did get that one correct. And here we have 1.32. I think that answer is actually incorrect. We'll take a look at it later. Oh, wait a minute, 2 times 6 makes 12. What am I doing over here? What's 2 times 6, guys? 12. So that's actually not, it's 35. Let's come back for a minute. I made a small mistake there. Like I said, you always make the smallest mistakes, little arithmetic mistakes. Look at what I did, 2 times 6. What's 2 times 6? Is it 18? No, it's 12. So 33 minus 12 is actually 23. Or this is really 23 over 25. And I bet you I made another mistake somewhere along the lines here. I can't really put my finger on it, but what matters is that if you carefully do it and look at the numbers, you'll get them right. This is 27 minus 18. That's right. It's supposed to be 9 minus 4. That's 5. Yes. There you go. What is 9 times 5? Times tables, Anthony. What's 9 times 5? It's 45. Okay, let's come back. 45 minus 12 is actually 33. So if it's 33 over 25, then you're going to get that figure. 33 over 25, which is 1.32. Okay. So I think you could see this is a lot. This is a lot. And I think it's probably kind of obvious. It wouldn't hurt for me to take a break too. So let me see here. Hold on. Okay, there we go. So what we'll do now is we'll take a short break, okay? And when we come back, we're going to carry on with our lesson. In the meanwhile, thank you so much for your close attention to this material. I can see, I know that it's challenging. I hope that you're able to follow it. But here again are the rules of the derivatives for you to look at. And now we have a little challenge. I'm gonna let you try to do that. See if you can figure out the answer to chapter 9.5, example 3 on your own. And when we come back, we'll reveal the answer. We'll do it together. Right now it's 5:41. We're gonna take a nice 10-minute break. I'm gonna ask you, please return and study with me again, my friends, at 5:51. All right, 5:51 we'll return. In the meanwhile, you got example 3 to play with. See you in 10 minutes. Okay, so here we have an example where we're actually adding together two things. And the two things that we're adding together, oops. One of them is one of our old favorites, 10x. We know how to do that. The answer is 10 to that. But the second thing we have is a big old quotient. We have to apply the quotient rule. So ultimately, the first real rule you're applying is the sum rule. The sum rule says if you have a function and it represents a sum, you're allowed to take the derivative of each of the things that are being added. There are two things here with a plus sign. So this is a sum. You can do the derivative of the first plus the derivative of the next. The thing is, when you do the derivative of the next, this piece here is a lot more work than the 10x. The 10x is, quick, easy 10, but this part becomes the whole quotient rules mess. So again, when you're doing a derivative, don't forget, if you have a revenue or a cost or a profit, and you're asked for the marginal revenue, cost, or profit, respectively, you're asked to really just find the derivative. So here's r of x. Let's find r prime of x. So it's going to be 10x plus 100x over 3x plus 5. All right, so let's carry on now. Finding the marginal revenue. This is the revenue function here. We want to find the marginal revenue. That means we're going to take the derivative of this function. So it's r prime of x. And now the sum rule says I could first do this piece. What's the derivative of 10x? It's 10. And now to take the derivative of this piece, I'm going to have to figure out what goes here. So I'm going to take a minute and kind of change my way of thinking and go into the concept of the quotient rule. The quotient rule works this way. F over g, if you're doing the derivative of f over g, it's like fg minus fg over g squared. But you have to do a prime on the f and then a prime on the g like that. So that means I need to define f. It's going to be 100x. I have to define g. It's going to be 3x plus 5. Then I need to state f prime. In the case of a constant times x, the derivative, as you might remember, is 100, is the actual constant. The x drops. Then to find the derivative of g prime, once again, the sum rule applies here. 3x plus 5 is the sum. The derivative of 3x is like 100x is the coefficient. It's just a 3. The derivative of 5, since 5 is a constant, we're going to let it evaporate, right? The derivative of any constant is nothing. It just goes away. So now we have fg, f prime, and g prime, and we're going to construct the derivative that will go into this piece of our answer using the quotient rule here. So the quotient rule calls for f prime, which is 100, times g, which is this expression, minus f. F is 100x, times g prime. G prime is 3. And then all over g squared. Now g is this expression here, 3x plus 5. So just write it this way. This is the derivative that goes in here. Let me simplify it a little bit. I can distribute 100 here and here. And then this is just the associative and commutative properties at work that make it 300x, right? This is going to be 300x plus 500. And then when we subtract them, they will cancel. Doesn't 300x negative and 300x cancel? Sure it does. And you're left with just this 500 here. All right. So what is going to go up there? 500 over 3x plus 5 quantity squared. This is what we're expecting you to come up with for the marginal revenue. I'm going to leave it there for a minute. And if you guys have any questions, you could either ask, you could unmute, or you could send a message. But I hope this is clear. As you can see, it's not just only the quotient rule. Now you're in a position where you're also involving other funny parts as well. So we have the quotient rule in here along with the sum rule. And now we're going from the revenue function to the marginal revenue, finding the derivative. All right, let's take a look at the next question. I think they're going to have you evaluate the function at a certain quantity, right? That's the marginal revenue function, and as you see, it matches what we have there. Likewise, they're saying find the marginal revenue when x equals 15, or when x equals 15. I would just put a 15 right into this position, right? And if I put that there, this becomes 45, and 45 plus 5 makes 40. So I have 40 squared, which is 1600. Well, I wouldn't put it like that. Say 10 plus 500 over 40 squared is 1600. So 10 and 5/16. Let's see what their answer is. Something like 10 and a half, approximately. See, what do they get for the solution for that? Let's see. Yeah, $10.20. So it is right on the money like we were expecting. Here you have 10 and 5/16. All right, so I hope that that makes sense. Okay, so in the next one, we're going to talk about the abstract idea of what happens when it's not clearly a constant, but instead of it being a number that we're familiar with, like 10 or 20, it's more so something like a variable, and we're told that it's a constant. So take a look at this question with me. It's a great application question. When medicine is administered, reaction measured in change of blood pressure or temperature can be modeled by this formula, where C is a positive constant and M is the amount of medicine absorbed into the blood. The rate of change R with respect to M is the sensitivity of the body to medicine. Find an expression for the sensitivity S as a function of M. This is a very long-winded story saying, please find the derivative of R as if you were doing R dr dm, or with respect to M. And the reason why it really is crucial here to know what that means with respect to M is because we have a new constant in the mix. We have C. This is the first time we're looking today at an equation that has 3 variables in it, right? Well, remember, it's really not a variable. It's not. C is not a variable. C is a positive constant. So what is the derivative of C? The answer is 0. The derivative of 100 was 0. The derivative of 5 is 0. Remember, we do the derivative of a half somewhere is 0. The derivative of any constant is 0. So when it's time to take the derivative of C, the answer will be 0. And you understand numbers in the real number system. C over 2, therefore, is also a constant. So when you take the derivative of C over 2, that's a constant. The derivative of that is 0. Likewise, C as a constant as if it were a coefficient. Remember when we had 100x and we said the derivative now must be 100? We also saw earlier 3x. The derivative of 3x was 3. So what's the derivative of cx? It's not the product rule, it's just c, because the derivative of something like that has an x is just its coefficient. That's going to come into play in this concept. So let's see now if we can find the derivative of r, dr dm, so that applying the idea of c being a constant, so that we could figure out the rate of change with respect to M. The answer, by the way, is going to look like this. I like to have that there handy. Before I go into doing that using some kind of product rule, I can see there is a cute trick there. I could just multiply them. Why can't I just multiply them? Doesn't it look like a distributive property case? So why don't we do that? So first, let me jot it down. Sorry, friends, I just got carried away there for a minute. Let's come back. We're trying to figure out the derivative of r with respect to m. So there's a couple ways you could write this. You could write this if you wanted to as dr dm, or you could just make it r prime. The easiest way to do it is just make it r prime. Now, I'm going to first rewrite this as if I'm using the distributive property to bring m squared through each piece. So it's I'm going to make it c over 2 times m squared minus, and then I can make this 1/3 m cubed. Now I need you to be all right to come from here to there. Why is this all happening this way? Well, if I'm multiplying this times this and I realize this is a constant, and let's just remember, this is a constant. That's really important. That constant really is like a coefficient for m squared, so I'm putting it in front. For this thing, whenever you have a fraction, you can always split it up in this way. Here's an example of that. The structure that goes along with that is if you have a over b, you can always make it a times 1 over b. It's the same idea. And often in calculus, you'll see things written that way, and it's easier to come back and make it a over b or vice versa. So you have to be kind of well-versed in which way to go to be able to get that stuff right. All right. So anyway, that being said, let's carry on with the derivative. We're going to use the difference rule here, which means I have a difference, two things being subtracted, and I can just take the derivative of this, and I can later on take the derivative of that separately. So let's do the derivative of this. We have a constant. So it's going to be that constant, and then I'm going to ignore it for a minute, and I'm going to focus on finding the derivative of m squared. That's the constant rule, right? Now the derivative of m squared is 2m to the 1. By the way, how many times have we done x squared, right? And then, of course, that's finished. Over here, when I do 3 times negative 1/3, I just get negative 1. And then I have m to the 2. All right, very good. Let's now carry on and simplify. 2 and 2 knock out. This looks like it's just cm now. And this is just m squared. This is the most direct way to write this. Another way you could have done this if you wanted to was you could have made it that this right here is the f, and this right here is the g, and think of it this way. And then do your product rule like this. Okay, now in this case, you'll notice, kind of like before with 1 over x cubed, when we showed you could do that in 2 ways, you could do this way with the distributive property first that I showed with m squared, or you could come in and let it be a product rule case and make one of them the f and one of them the g. If you wanted to do it that way, you still would get this as your answer, but you do a lot more work. It would be much more involved. It would involve derivatives of complicated expressions, and you might make a little mistake. So the best approach is really to take the strongest path, the quickest path and the easiest path in calculus, because usually there are many paths and often most of them are really bad. The best way to go is to see if the person who came up with the question put some kind of trick in there to make it easy. In this case, there is a trick in this one. If you do the distributive property first, it actually comes out to be very basic. If you do it this way, though, you'll see it does get very, very complicated, but it does finally algebraically come back to being this. All right, so that's the story of the blood and the drug in the blood and that whole thing. By the way, a word about critical thinking when it comes to word problems in calculus. I always try to advise my students about that idea, because math already has challenges in it, but to add words to it, a lot of students have it gives them anxiety. It's a bad thing. So let's talk about this word problem for just a minute. What if you were faced with this word problem? How would you attack it? Well, first of all, I do not claim to be a nurse or a doctor or a phlebotomist or any kind of hematologist or anything about blood. I also am not familiar with pharmacology and medicine and such and all these ideas. But I do know math, and I do get it that this is in the chapter of finding derivatives, and probably the answer is find the derivative. And what happens is, as you do all of these different applications, this one is about blood and the drug in the bloodstream. The next one will be about a planet. The next one will be about something in economics with the stock market. But each time, again, it's an example of the derivative, which starts to get you accustomed to what different applications in the real world do apply to this concept of the derivative you learn. And that being said, I don't really need to understand particularly that when medicine is administered, the reaction is measured in the change in blood pressure. I don't need to know any of that. What I need to know is I need the rate of change of r with respect to m. That's all I need. That's all I need. After you see that, the rest of it doesn't even really matter. If you do that part of it right, you're home free. The only curveball is when you see one extra variable, go and look through the word problem and try to figure out what each variable means. Look closely. They're telling you that reaction is what the R is. They're telling you that M is what the sensitivity is. And they're telling you that C is a positive constant explicitly so that you can go in the direction of, oh, this is a little test about, do I understand the derivative of constants? Do I understand the derivative of coefficients? And things like that. So just remember, friends, this question, when you come up with a weird question that's a word problem, please come back and remember our ideas today. Also, if you ever come up with a question that has 3 variables, this is a great example of how to apply it. Usually if there's 3 variables, one of them is a constant variable and you have to act like it's a constant. One last thing about this question that might make it easy on you, if you're doing a question like this and it really is hard to grasp that C is not a constant, what you could do to make it easier on yourself is just, instead of writing C, change it into a number and just leave it as a number that's hard to change around so that it never interferes in any way. Like, say, for example, maybe you made it 17. 17 is a really ugly number. Like 17 is not going to combine with 3 nicely or with 2 nicely or something. But if you write this all out and you think about, oh, if it was 17 over 2, then yeah, it would be 17 2's n squared. And then I think I know what I do, but I think in a lot of times having that C is just such a block. If you really can't see past it, friends, go ahead and imagine for a minute a number in that position, and then you'll know what to do. If it was 17 2's, I'd know what to do. C over 2, I don't know, but 17 over 2, oh, I get it. And it's also about that boldness of realizing that you got to treat it like it's constant, which you feel like it's a letter and you kind of breaking rules. So that's another thing we have to focus on in this chapter. Okay. All right. So now we're going to talk about the chain rule, and we only have about 20-25 minutes left to our lesson, but the good news is the chain rule is kind of quick. Like I said, it's abstract, and if you don't really quite understand it today, that's okay. The next time we hang out and talk, we'll explain it and we can do some examples of it. Again, I'll be here tomorrow if you want to study, only if you need me. But before we do the chain rule, you have to remember this idea of something you learned in algebra called composing functions, or composition, or composite functions. Look very closely, friends, at this very beautiful little symbol. Hold on, I'm trying to get my, okay. Here we go. Look at this one first. I don't know why they tell you G. Look at the one I put in the purple box. This little beautiful circle is very much like your degrees from geometry class, but it's not all the way up the way that 90 degrees has it up there. It's kind of in the position of a plus sign or a minus, because it is an operator, it's an operation. Like plus, minus, or divide. You could divide functions or add them, you could subtract them, and of course you could compose them. And when you compose them, you do something a little different. You take one of them and put them into the other. You stuff it into the other. You might have seen diagrams in your algebra book of a function machine that looks like a factory with like an opening that you put something in it and it comes out an end on the other side and things like that. The point is that it's supposed to be that you're taking a function in its entirety and putting it directly into the other place. One of the easiest ways to see this is, like I explained before with the C and the 17, is to consider the functions themselves and the letter X to have a symbol or something a little bit odd. Let's take a look at example 1. I'm going to write it down and then I'd like to explain how it works. Okay, so we're trying to find F compose G. That's how you say this out loud. It looks like fog. It's kind of funny. F compose G. The way you do F compose G is you find F of G of X. And I'm going to put G of X kind of like in a different font in a different way here so that you can see that what I mean is this whole thing goes right there. Okay. And by the way, what is a function anyway? F of X equals 3x squared means that if I knew that this was a 6, I could put a 6 here. And I could say, oh, you mean to calculate 3 times 6 squared? Or if I put a 7 here, oh, you mean 3 times 7 squared? So what if I put a 2x minus 1 there? Well, you mean to put it there. So if the x is bothering you, make it f of the cloud. And I've written this on a chalkboard a billion times in my career, the cloud concept. Whatever is in that function, the directions of f are to do 3 times that squared, whatever that is, whether it's 2 or x or whatever you want to call it. For example, f of x would be 3x squared. And that's really ultimately just an example. Now, when you do composing functions, you have to think about how f compose g means f of x means f of g of x. So you put g of x in here. The first step is to write it like this. And then to put this right into the formula of g. Of f, I mean. Okay, so here's f. Right in that cloud, I'm going to put this. So it looks like this now. 3 times 2x minus 1 squared. This is what it means, friends, to compose functions. You take one of them and put it in its entirety into the other one. Now, when you do it, sometimes after you do it, there's more work to do. Like you might want to multiply this out and square this out and do the binomial of 2x minus 1 times 2x minus 1 and then FOIL and all that. Or if you go in the opposite direction, sometimes you could see it's easy to go. But it is important when you're done to look and make sure that one of them looks like it's fitting into the other. Take another example of this if we were going to go the opposite way. If we were going to go the opposite way. And instead I was going to say, find G compose F of X, right? To find G compose F of X, it would be something more like this, G of, and then F of X. Now what is F of X? F of X is 3x squared, so this is G of 3x squared. Now what is the G rule? G tells you to do 2 times whatever minus 1. Right? With the cloud, it would be 2 clouds minus 1. So it should be 2 times 3x squared minus 1. And then, of course, this becomes 6x squared minus 1. That's what we would want for G compose F. By the way, please note, it is not commutative, meaning G compose F is not F compose G. And that's really important too. Sometimes it is, very rarely. If it is, that means something else. That means the two functions are inverses, but that's another story. For now, all you really need to know is generally, usually, it is certainly very different. G compose F is and F compose G. All right. So that's what it means to compose functions. And the reason why we're talking about how to compose functions is because the chain rule does follow the concept of composing functions. And like I said earlier, if you don't really quite understand it the first time, that's okay, because after you look at it a couple times, it'll start to kind of make sense. So anyway, here's our final solution for that one. And that's what we got before. All right, and this is the chain rule. So the chain rule is saying if f and g are two functions, and it's kind of like they're composed, you know, it's hard, it's not really written very clearly, but if they're two functions being composed, then you can act as if you're just taking the derivative of it, and then later on take the derivative of the function that's inside. So if you're doing f compose g, g is the function that's inside, just do the derivative like you always would, and then add on the derivative of what's inside. So let's take a look at example 2. Example 2 is using the chain rule. Find dy dx. Again, a fancy way to say, please find the derivative. So it's y equals example 2. Y equals the square root of x squared minus 1. Find dy dx. Okay. Meaning find the derivative of this function y with respect to x. So dy dx we could find, but first I'd like to call it this. Okay, now you might remember square root means power of 1/2. I don't know how to multiply this out. Of course, 1/2 is a funny exponent. I've never done anything like that with it. So here's how I'm going to handle it. I'm going to apply the chain rule. This is kind of like two functions being composed. The first function is x to the 1/2. or cloud to the 1/2. The other function, of course, is x squared minus 1. So here's what I'm going to do. I'm going to act like it's the cloud to the 1/2. If it was cloud to the 1/2, then the derivative would be 1/2 of that cloud to the power negative 1/2. And that negative 1/2 is up there because it's 1/2 minus 1. Let's do that real quick on the side. What is 1/2 minus 1? Well, remember, 1 is the same as 2 over 2. So 1 minus 2 is negative 1. That's why it's negative 1/2. Remember the power rule. But now here's where the chain rule kicks in. I still haven't really kind of justified doing this. This is not x, it's a cloud, and it's something bigger than x. It's x squared minus 1. So the way you deal with it is first you treat it like it's x. If it was just x to the 1/2, it would be 1/2 x to the minus 1/2, but it's not, it's the cloud. So now the chain rule is as if you have a new link on the chain, like you're adding a link to the end of a chain. Now you add the derivative at the end. What's the derivative of what's inside here? Here, what's inside the derivative would be 2x. And don't forget the derivative of negative 1 is 0, right? So it's just 2x. In other words, times 2x. The derivative is all of this together, right? This is just an idea, by the way, but it's all of this together. 1/2 x squared minus 1 to the negative 1/2 times 2x. If it helps, you could put each of these things over 1, and then you might notice that these things cancel out from afar. That's the commutative property at work. And since they knock out, your final solution is this times x. You might want to write it in front. If you wanted to write this again without negative or fractional exponents, it would look like this. X would be on the top, of course, because it doesn't have a negative exponent. X is just x, so it's a top number. But then on the bottom, I would give it a square root like that. That square root means to the negative 1/2 power because it's a root is the 1/2, and because it's in the bottom is negative. So if you wanted to rewrite it just once more, the derivative actually does look like that. This is an extension of more algebra that you already should kind of know. It's not the chain rule. The chain rule is really this piece that after you look at the function and you say, I know I could do this somehow. How can I find the derivative of this? You have to act like it's the square root of x. If it was the square root of x, you'd know what to do. But it's the square root of an expression. So it's like a pair of composed functions, and you have to apply the chain rule. And by the way, with the power rule is what we're talking about, how it's to the 1/2 and how it still is a cloud and it represents a power. All right. So that's our answer for example 2. I hope that helps. I hope that's clear. And if you wanted to go all the way, that's what it would be. Right? And now we have a very weird abstract one that involves many DTs and DLs and DWs. I'm going to read it out loud. Try to focus on it with me. The relationship between the length L and the weight W of a species of fish in the Pacific Ocean is given by this formula. The rate of growth in length is given by this formula. And notice it is actually a derivative they're giving you. And they're also telling you T is in years. And they want you to figure out dW dt in terms of L. This is pretty extra. There's a lot of variables and there's a lot of different derivatives. So let's try to write them out in a really clear way. First, what I'll do is I'll write down what I know out of the word problem. What I know out of the word problem is W equals 10.375 L cubed. And dL dt equals a very strange expression, 0.36 minus 0.18 L. And we're trying to figure out dW dt. Okay, so we've really got a lot going on here, but one thing that we can do is, since we have an equation that is given in W and L, that does tell us that we're in a position to find dW dL. Let me just come around and figure that out. That's not going to be hard to do. dW dL ought to be 3 times this figure. Do that real quick. 10.375 times 3 makes 31.125. and then lower it, right? Okay, so I want you to look at all these different things. Now we're trying to figure out dw dt. We're trying to figure out dw dt. Wouldn't it be clever if we could use this idea and this idea to come up with dw dt? Look very closely. If I write dw over dl times dl over dt, look what happens. And it solves and it's correct. This is a kind of embedded word problem. It's kind of deep. I want you to make sure you come back to this word problem when you're doing your web design homework, when you see situations where you have 3 variables and more than 1 derivative. This is how you handle it. The thing that they give you is the dead giveaway of where you're supposed to go next. You know, the W equals something in terms of L means that you have means to figure out what is the dW dL. And when you figure that out, you can use that and the other derivative in a fancy way to get everything to collapse and knock out just right to get what they're asking for, which is dW dt. According to this model, I should be multiplying these 2 things together. So what happens when I multiply this times this? It's going to be a distributive property, isn't it? It'll be this number times 0.36, which is 11.205. And that's L squared. And then 31.125 times negative 0.118. I'm sorry, 0.18, right? 5.6025. And then L cubed. This is the answer they're looking for a question like this. Pretty extra, isn't it? And they wanted it in terms of L. Notice everything is all just L's, and it does make sense. So I hope that helps a little bit. In this case, you're kind of doomed without a calculator, unless you want to go back to the 2nd and 3rd grade skill sets of using a pencil to do arithmetic. I would definitely have a calculator handy. Most calculators are right on your, you don't even have to go to Desmos for stuff like this. I would just use the basic calculator in your computer. All right. All right, great. So that's what we were looking for. As you could see, very complicated to answer, but that's what they want. Also, a word about, oh, by the way, there is one last thing. If a fish weighs 30 kilograms, approximate its growth. Okay, that means put, of course, that means put 30 as your number right here in the L's and get your solution. You'll get this, right? All right, so some of that's clear. Okay, so now where we are is we have about 10 minutes left to class. And in these last 10 minutes, I'd like to show you a couple of little quick derivatives, and then we're going to quit for the day. Here we have an example for example, for A and B. We're trying to figure out a couple of different derivatives using the chain rule. Let's go through those. It probably will take all of about literally 10 minutes. So part A. This is example 4. It's going to be y equals x squared minus 4x to the 6th. The next one is p equals 4 over 3q squared plus 1. Okay, the first one, we're going to act like it's a cloud to the 6th. If it was a cloud to the 6th, then dy dx would simply be that cloud, but first it would be a 6 and then the cloud, which is this expression, and then we make it to the 5. Now we need the derivative of what's inside. It's the chain rule, as if there's another link to add to the end of the chain. The derivative of this inside is, and use multiplication, so just use parentheses, the derivative of x squared for the 10th time today is 2x, and the derivative of negative 4x is negative 4. That's it. Good enough right there. If you want, you could distribute the 6 through the 2x minus 4, but frankly, it's really kind of a waste. Later on, you might have to just factor it back anyway for some reason. Just leave it the way it is. Furthermore, WebAssign will take many different versions of the answer. Like I said, the chain rule is hard to understand at first, but when you see the pattern of it, it's actually really pretty simple. Just imagine it's a cloud. If it was the cloud to the 6th, it would be 6 cloud to the 5th, just multiplied by the thing that's inside later. The same thing's going to happen here with this situation. In here, before I start applying that nasty, horrible quotient rule, let's see if we have any tricks up our sleeve. Aha, we do. We know how negative exponents work, so let's use negative exponents. Right now, P can also be written to be 4 times that expression to the negative 1 power, because it is ultimately really to the 1, and it is down in a denominator anyway. So if we were going to do 4x to the negative 1, you know what you do. You do 4 times negative 1, and then you do negative 1 times minus 1 again, and you get your negative 2. So let's do that. Let's do that. dp dq, meaning the derivative of p with respect to q, dp dq, however you want to write it, or you could call it p prime if you want, is going to be 4 times that cloud to the negative 2. Why is this negative 2? Because you have to say negative 1 minus 1 is negative 2, just as a reminder. All right. Now, after you write that, you have to think about what is the derivative of what's inside. And here we have 3 times q squared. That's going to give you 6q. And what's the derivative of 1? Remember, it is nothing. So here's your answer. Let's write a little bit nicer. Maybe I could put the 6 and 4 together. 24q. And that's a negative 2. Let's put it on the bottom where it goes. That. And there's your dp dq. Can you see that? What do you think, guys? I hope that's clear. If you want, you could do f over g and make it the quotient rule, and f is 4, and g, blah, 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 blah. Guess what you'll get? 24q over blah, blah. All right. Now let's go back and take a look at our lesson. Here are our solutions, as you saw earlier when we went through them. And there's the other one. I think I forgot a negative in there, didn't I? Yeah, I did. There should be a negative in there. Let's just come back. See, when I did negative 2, there should be a negative in there. Because when I did negative 1 times 4, that was supposed to be negative 4. I forgot that negative. That's why the answer is negative 24. Just a little mention. Just watch out for those little mistakes. It's kind of important. All right, back to our lecture. And here we have find the derivative of these 2 things. In the last 5 minutes, I'm going to see if I could crank those out. Let's try. First one is yeah, I know we only have 4 minutes left, but watch this. It's 3 times, of course, that expression to the 1/3, right? All right, so if the cloud was the parentheses, 1/3 times 3 is just 1. So y prime would start with just a 1, and then it would be that whole expression again. And then I need to figure out what is 1/3 minus 1. Well, it's the same as minus 3/3, isn't it? Oh yeah, we did this over and over. What's 1 minus 3? It's minus 2. Minus 2/3. And then the chain rule times the derivative of what's inside. The derivative of what's inside here, this is 2x. What's the derivative of x squared? 2x minus 3, right? Want to put them all in one fraction? Okay, so it would look like this. 2x minus 3 goes on top. Since this is negative, it goes on the bottom. And since this is 2/3, that means it's a cube root here. And it also means that it's squared like that. Very ugly looking, but that's what it would be. You could also have just rewritten it the way you see it here. WebAssign will take it just like this. I mean, don't put the 1, but WebAssign will take it just like that. The other one in our example is 1 over x squared plus 1 g of x equals 1 over x squared plus 1. But on the bottom, we have it's being cubed. And it's got a square root. Okay. Now, hey, that looks kind of familiar. Didn't we have something kind of like that when we did it here? Remember when we had a cube root and a 2 exponent? It was 2/3, because the 2 on top is the exponent, 3 on the bottom is the index. Okay. So this is negative, so I can make it, of course, first x squared plus 1 to the -3, right? But there's a root there. That root is like a half, so it's -3/2. So now you could apply the chain rule and pretend the cloud is x squared plus 1. G prime of x would be, take the coefficient, make the exponent the coefficient -3/2, and then write the cloud. And now figure out -3/2 minus 1. Okay, don't give up. -3/2 minus 1. That's like -3/2. -2/2. It's the dreaded -5/2. Yes, it is. And last but not least, the chain rule says, take the derivative of what's inside. What's the derivative of x squared? Again, it's 2x. Derivative of 1 is nothing. If you want to simplify this a little bit, the 2's will knock out, and you'll have on top just 3x. And on the bottom, you'll have x squared plus 1, using the 2 as a root, and using the 5 as an exponent. By the way, the thing is negative. Take a look there. Hey, guess what? It's 6:44. I'm still within 6:45. Can you believe it? Well, anyway, that's our answer. All right, I hope that makes sense, my friends. Just to check alongside, here are the answers. As you can see, they're just as ugly as they were before when I was telling you them. And I hope that today's lesson was helpful for you. There is one more example. I'm not going to do it. Don't panic. I'm not going to do it. But we can do it when we get together tomorrow if you want. It's ultimately just the same thing all over again. Try it one more time if you want. It's P is the price in dollars. Find the rate of change when P equals 24. You go through the motions of finding the derivative. Then when you're done, you plug in 24 and that'll give you the answer. Right. So in closing, friends, I hope that was helpful. And there's a lot of stuff in that chapter. Like I said earlier, that's the wrong date. That's, of course, I used the last year's one and I edited it, but hope that was helpful. I'm going to dismiss now. We're going to stop the recording, and then we'll open the floor to questions. Thanks again, friends, for your attention. I do appreciate it.